All right, let's get right into it. Today, we are stepping way beyond the boundaries of your traditional kitchen and crossing the threshold into the rigorous laboratory of taste. We're unpacking the profound, highly technical universe of Chef Davu's The Sugar Bible. Now, if you've always thought of sugar as merely a sweetener, just something to make things taste good, you need to prepare to have your culinary paradigm completely shifted. In the realm of advanced modern pâtisserie, sugar isn't just a flavor. It is an active chemical reagent. It's a structural engineer. And mastering how it actually functions on a molecular level is exactly what separates a standard cook from a true culinary architect.
Here's our syllabus for this explainer. We'll kick things off with the atomic architecture, then rigorously compare PAC versus POD. From there, we'll analyze isomalt's role in 11-element desserts, meticulously track thermal decomposition thresholds, and finally wrap up with the Masterclass conclusion.
Section 1. The atomic architecture. Because to truly understand the macro structures of high-end desserts, we absolutely must master the atomic foundation first.
The foundational concept we really need to wrap our heads around here is water activity, which is mathematically denoted as AW. Think about a complex dessert, specifically those massive centerpieces boasting 11 or more distinct elements. In those systems, every single gram of sugar chemically alters the water activity of the entire dish. It actively binds with unbound, free-floating water molecules. By doing so, sugar acts as a microscopic structural engineer. It dictates the preservation limits, it aggressively modifies texture, and it forces us to finally recognize that sugar is a highly functional solid, not just some passive flavor enhancer.
And understanding that water activity brings us directly to a very real kitchen nightmare, syneresis. Because sugar is fundamentally hygroscopic, meaning it has an exceptionally high affinity for drawing in water, it basically acts like a molecular sponge. In high humidity environments, which Chef Davu brilliantly refers to as the village office context, this sponge effect can be totally catastrophic. If hygroscopy is imbalanced in a multi-element masterpiece, sugar will aggressively pull moisture from a wet element, like a delicate cream, and just dump it into a dry element, like your sponge. Preventing this syneresis is absolutely vital for structural integrity.
So, the crucial point here is understanding the bond itself. I want you to mentally observe the exact molecular geometry of sucrose, C12H22O11. Picture the physical architecture in your mind. One rigid alpha-D glucose ring bound directly to one beta-D fructose ring. That bridge connecting them? That's the glycosidic linkage. Visualize that exact covalent bond right now, because when you apply intense heat to create a syrup for, say, a mousse, that linkage is severely stressed. The precise speed at which those molecules break apart and realign, the crystallization science, will dictate on a microscopic level whether your final texture is unpleasantly gritty or luxuriously silky.
Section 2. PAC versus POD. Let's delve into the specific molecular weights and chemical functionalities of these highly technical sugars.
This right here brilliantly illustrates why standard table sugar is functionally obsolete in modern frozen patisserie. We are comparing dextrose, which is atomized glucose, with standard sucrose. Every sugar in the professional kitchen is measured by two metrics: its POD, which is its sweetness power, and its PAC, its anti-freezing power. Sucrose sets the baseline with a POD of 100. Dextrose, however, has a significantly lower POD of 70, meaning it is noticeably less sweet. But it possesses a staggering PAC of 190. That massive anti-freezing capability is simply non-negotiable when you're formulating high-protein elements or complex frozen desserts.
And it all comes down to this specific temperature, exactly -18°C. This is where the PAC logic proves its absolute necessity. Because dextrose is a monosaccharide, a single highly mobile molecular ring, its sheer molecular weight and structure allow it to physically interfere with ice crystal formation far more aggressively than the much larger disaccharide sucrose. By utilizing dextrose, a pastry chef can mathematically ensure that high-protein, deeply frozen elements remain perfectly, smoothly scoopable at -18°C, entirely bypassing that terrible crystalline rigidity that standard sugar would cause.
Section 3. Isomalt in 11-element desserts. Let's see how these specific sugars act as the structural glue in multidimensional masterpieces.
When you are constructing just 3 components of an 11-element dish, like Chef Davu's renowned The Dark Forest Awakening, notice the incredibly rigorous Brix balance required. Brix, of course, is the measurement of the dissolved sugar-to-water mass ratio. For the core, we utilize dextrose to achieve that precise soft melt we just talked about. For the mousse, we employ inverted sugar, specifically trimoline, where heat and acid have completely severed that glucose-fructose bond, because its humectant properties lock in water molecules, ensuring immense stability and preventing recrystallization. And finally, for the garnish, we rely on isomalt. Every single element demands a scientifically calculated sugar concentration to guarantee these components do not organically bleed or leak into one another over a prolonged service time.
Now, let's isolate isomalt for a second because its chemistry is truly fascinating. Isomalt isn't actually a traditional sugar. It is a polyol, a sugar alcohol derived from sucrose, but subjected to intense chemical modification to achieve extreme structural stability. Its defining characteristic is that it is fundamentally non-hygroscopic. It literally violently rejects ambient moisture. So if you are constructing delicate, glass-like coral toulis or translucent sugar spheres that absolutely must remain structurally sound, visually flawless, and bone-dry under the intense heat of professional service lights, isomalt is scientifically the only viable choice.
But to successfully manipulate this polyol, a chef must operate with astounding, laboratory-like thermal precision. The initial phase transition, the melting, occurs strictly between 145 and 150 degrees Celsius. However, if you want to achieve that supreme optical-grade translucency required for high-end garnishes, the thermal load must be deliberately pushed to a maximum clarity processing window of exactly 165 to 170 degrees Celsius. Deviate from this precise working temperature, and the molecular structure literally collapses into a cloudy opacity.
Section 4. Thermal decomposition thresholds. We must now look at exactly what happens when sugar degrades under extreme heat.
Let's meticulously track the chemistry of caramelization, which, let's be real, is strictly the thermal oxidation of sugar devoid of enzymatic activity. In phase 1, between 100 and 110 degrees Celsius, we experience pure evaporation. Unbound water escapes, and the Brix density spikes. As we push to phase 2 at exactly 160 degrees Celsius, we hit the light caramel stage. This is where the magic really happens. Immense molecular fragmentation occurs, breaking the sugars into hundreds of volatile aromatic chemical compounds. Finally, we reach phase 3, the critical zone between 175 and 185 degrees Celsius. This is the dark caramel phase where active carbonization begins. The molecular chains are literally burning, developing very specific bitter notes that are scientifically required to balance the overwhelming sweetness of an 11-element dish. Now, controlling these violently volatile carbonization stages is incredibly unforgiving. I mean, if you overshoot 185 degrees by even a little, your complex compounds instantly turn to pure acrid carbon. This is exactly why professional environments demand the unwavering exact thermal environmental control of the UNOX oven. The UNOX oven's thermodynamic precision ensures that the ambient heat transfer to the sugar is mathematically constant. It prevents what we call caramelization failure, where uneven oxidation completely ruins the chemical balance of the entire dessert.
Finally, Section 5, the Masterclass conclusion. We've journeyed from atomic architecture all the way up to thermodynamic oxidation.
दोस्तों, ये थी शुगर की वो केमिस्ट्री जो बड़े-बड़े होटल किचन सीक्रेट्स में छुपी होती है। मैं आपके लिए ये इतनी मेहनत और डीप रिसर्च इसलिए कर रहा हूं ताकि आप सब एक प्रोफेशनल शेफ की तरह सोचना शुरू करें। एक एक्सप्लेनर बनाने में और ये टेक्निकल डेटा आप तक लाने में बहुत वक्त और एनर्जी लगती है। अगर आपको लगता है कि आपने आज कुछ नया सीखा है तो प्लीज़ लाइक, कमेंट, शेयर और सब्सक्राइब करके मेरी हेल्प करें। आपका एक सपोर्ट मुझे और भी बेहतर कंटेंट बनाने के लिए मोटिवेट करता है। कीप लर्निंग, कीप बेकिंग। अगले एक्सप्लेनर में मिलते हैं। But before we sign off, I'll leave you with this one thought. If a single molecule of dextrose can completely rewrite the laws of how ice behaves at negative 18 degrees Celsius, what other massive chemical secrets are quietly hiding in plain sight inside your refrigerator right now?